All right, so this morning we'll pick up where we left off last week with the discussion of the concept of the rate law, the rate equation of a chemical process, which is cast in the form of a differential equation. Now, we also distinguished between two elementary reaction type, namely the unimolecular and the bimolecular processes. In this lecture, we're going to elaborate a bit further on the elementary reactions, right? Since these are very important in understanding the more complex mechanisms, because they form the building blocks of those mechanisms. So before we move there, it's best to first get a thorough understanding of the elementary reactions, and we start with first order reactions. Now, the rate equation for a first order reaction, which is one of this type, compound A goes to B. You can think of the, as an example, of the cyclopropane reaction, which only involves a single molecule that converts into propene, a more stable form of that molecule. Another important class of processes that follow first order kinetics are radioactive decays, where a radioactive nucleus, an unstable atomic nucleus, has a certain probability within a second or within an hour to decay into something else, which is also formally, in mathematical terms, a unimolecular process. Now, the reason why the rate equation looks like this is that at any time you have a certain concentration or number of A molecules or nuclei, whatever they are, then the amount of them that subsequently undergoes conversion to product within, say, 1 second or 1 hour, or dt, a time interval dt, will of course be directly proportional to the amount present at that instant. If you double the amount of radioactive nuclei and see what happens in 1 second or 1 hour, the number of decay processes will double with it. So vary in proportion to how much is there at any given instant. That proportionality is written formally in mathematical terms as the rate of change, the decay rate of the nuclei, is a constant, so it's proportional to what is there at any particular time. Now, this is a mathematical equation, a differential equation of a type that can be easily solved or integrated, as we saw. So the issue now is to use the mathematical technique of integration to find out what, for a given starting concentration at time 0, so A at time 0, what the concentration will be at any future time. Now, that the information is contained in the differential equation can be seen easily if you multiply the equation on both sides by dt, cancelling it here and putting it there. Right? What that gives you is the drop in concentration minus dA during that time interval dt, when at the start of that interval the concentration was A. After the interval dt has elapsed, there will be K times A times dt less of it. So we now have a new starting concentration, right? That now is the input for the calculation, a similar calculation that tells you how much will be left after the next dt. So that will be K times the A concentration at T plus dt multiplied by dt, and so on. So you can just go stepwise, follow the process in time, in small steps, dt. At each step you know how to compute the amount of A lost, so the amount remaining is known. and that therefore predicts the future time course of the concentration of A, right? That is the idea behind the differential equation. Of course, that's a bit awkward. If you want to go about solving it in that way, it would be much better if we have a single expression for A as a function of time, which is the solution of the differential equation. So the question is, how do we go about solving that equation? Right? Now, how to go about it, you will I'll first have to crave your indulgence as I digress a bit on the on the relevant aspects of the calculus. There are a few rules that you need to know, or you should know already. First of all, we're going to be using logarithms a lot. A fundamental property of logarithms. Okay. This one, you see it now? All right, so I have the pointer now in place. Okay, good. So if you have a logarithm of a product of two vectors, x and y, then the logarithm splits it into a sum, a log of x and a log of y. And conversely, of course, if you consider that sum, you can combine the logarithms into a single one with as its argument the product of the arguments of the individual terms. Right? Now, as a corollary really of this property, we have this rule that the ln of x raised to an index a is equal to a times ln x. So what you do is you take the index and you put it in front of the log, right? You can see that, for example, with a equals 2 when you have a square. Now the ln of x squared is the ln of x times x. So that would correspond to x equals y here, right? So that becomes ln x plus ln of y, which is 2 times ln x, right? So indeed, the same rule applies, and by induction, you can show that to be true for any integer value of a, at least. Now, the operation of differentiation, which obviously is very important here, because what we are in the rate equation, there appears on the left-hand side the derivative with respect to time of a concentration, right? In this case, this is written more generally as the derivative of a function f of x, with respect to the running variable x, df by dx. We call that the derivative, and we use a symbol lowercase f to indicate that. So there is a one-to-one correspondence between the capital F and the lowercase f. So lowercase f is called the derivative of capital F. Capital F is called the antiderivative or integral of lowercase f. Now, of course, this df by dx is formally a quotient, df divided by dx. If you have an, or let me see if I can use the white at this point. I was trying to avoid that, but share blank. Hello. Blank whiteboard. Right. Okay, so imagine the following. I always find this whiteboard a bit awkward to use, but let's try it anyway. Oh, what is this? Yeah. Well, okay. So suppose that we plot, what is this, text? X is the variable fx. That is the function, and let's just draw an arbitrary function like this. Whatever, right? Now at a point x, an arbitrary point along the, oh, I should have used a straight line option, but okay, it's straightened itself out. No thing, I want text. No, so call this point x. Yeah. Then df by dx has the geometric interpretation of being equal to the go back to this. Yeah. Oh, anybody else has a problem of not seeing anything on the whiteboard? I mean, I'm drawing on it now, but just give me some feedback. Oh yeah, okay. Everybody else seems to be able to see it. Okay. Right. Bang. Oh. Trying to get rid of this now. It's very time consuming, but at least it gives you some time to reflect on this. Okay, now I'm gonna put in some text. So the rise is df, the run is dx, right? But df upon dx, what is that equal to? Well, it is equal to the gradient slope of the tangent to the curve at that point. All right. Right, the tangent, which is the linear approximation to the curve within a very narrow range, yeah, x plus dx. So df by dx is the gradient of a tangent. Now df by dx is the, we saw the, is the, what do you call that, the derivative, lowercase f at point x, right? So we could also plot f as a function of x. Where are we with that? Bang. Yeah. This thing just works very intermittently. Okay. See if I can do a next one here. Yep. So again, you have x here. And f, well, the lowercase f up there. Right? And that is some, well, a function that is governed by the variation of the gradient of the upper curve with x. Well, don't know exactly what it would look like. Yeah, so this might be it. So here's the same x. We get that straight line again. Bang. What's wrong with this thing? Bang. Right. And here we write the dx beside it. Yeah, so the next one is x plus dx. Right? This is x plus dx. Now if we write this expression here differently, so write it as df equals, and we'll leave some space here, fx dx. Yeah, same as that. Now we see that in this graph, df is the small increment, the small rise in the capital F function, right? In the lower graph, the same numerically the same quantity is equal to fx times dx. Now fx is the height of this rectangle, right? It's the function value of x. dx is this base here. So fx times dx is the interpretation of an area, the area of this vertical strip, right? So we have now established that the increment in capital F is equal to this area under the curve fx. All we need to do now is do that at every x and add up the resulting increments. So what we do essentially is we sum on both sides of the expression, and the sum runs from a value of x equal a to a value of x equals b. You know, you can imagine that easily. But what it comes down to is that the left-hand side gives you the sum of these increments, which means the overall rise in the curve. Or if the curve goes up and down, it will be the net change in elevation of the capital F function between 2 points x equal a and x equal b. Yeah. So if we plug that in here, so say x equal a, x equals b, same limits here, a, right? Then what we have is that this is also equal to whatever the capital F is at point B minus its value at point A. So the overall increment, in line. Let me just run this line across. So this is, say, point A. And say this is point B. No. So let me just finish this picture because that's the worst part of it, right? So we started off with a function fx with this curve. df by dx at a point x, right? df by dx is the gradient of the tangent. Yeah? df by dx, of course, is variable itself. It goes from one value to the next if you move along the x-axis. If you make a graph of that gradient, you end up with something like this, right? So this lowercase f is what we call the derivative of capital F, right? Right, so this plot is the derivative, so is the value of the gradient at each point along the capital F. And we draw the graph between points x equals a and x equals b. Now at some intermediate point, x, yeah, right, you look at what happens in the increment dx. Yeah, so you move from x to x plus dx. That means if you move along the curve fx at the top, okay, right, okay, let's go over this again. So fx, that is the function, which is this curve here, right? Right, so this is the at point x with function value fx. The gradient of the tangent is df by dx, the rise over the run, which is what I've written here, which is itself a function of x, which is plotted down there, right? Yeah, so this is the relation between capital F and lowercase f. Now what happens if we multiply? Yeah, okay, there's a question here. Casilla, go ahead. Say something.
Hi, good morning.
Hi, morning.
Are you able to see my pointer?
No, I only see my own. So I'm not sure if you
I
are
was
authorized
wondering.
to. I think it's a setup that none of you are able to write on that whiteboard or do anything with it. So that's just because of the sheer numbers. I have no control over that. I'm not. Yeah. So
Okay,
you were
sir, I
trying to point at what?
All right, my question is, the two lines A and B,
The
are they
verticals, yeah.
connected to the two graphs? Are they connected?
No, that's just because I was lazy. I just didn't want to draw the same thing twice. So there's
Oh,
really an
okay.
A here and a B there, right? So don't read too much into it.
Okay, sir. So the
Yeah.
first graph, we're just finding the gradient, the
Right.
triangle.
Right. So that is just the if you move in the x direction to return back to the curve, because you leave the curve here. If you want to return to it, you have to go up by df, right?
Oh, okay.
Yeah, and the
Sorry,
amount by which.
continue, sorry.
Oh, okay. So by the amount by which you have to go up at point x, divided by the distance through which you went to the right, dx. If you divide this by that, you get the gradient of the tangent, right? Which is the derivative at point x. And there's a different value, of course, as you go along the curve. Now, that's how you end up with this curve here. If you plot those gradients, values of the gradients as function of x. Now, the idea behind the calculus is that if you multiply both sides of this expression by dx, so cancel dx here, put a dx there, you're left with the df here, this increment. In the bottom curve here, you have the fx, this fx, multiplied by dx, which is the area of that rectangular strip that you see over there, right? So what we have established is that if you go back to the antiderivative of this one, this increase, df, is equal to this area, f dx, right? And then you just sum. And then you just take a sum running from here, from A to B. And that is what this symbol means, which is an integral. It's really an elongated S. Yeah? And you do that on both sides, of course. So what you get on the left is the total number of increments in F, which is basically the overall rise going from A to B. Or if the curve goes down, of course, that means a negative contribution. But what you get is the overall difference in the function value fb minus fa. Right? In the lower curve, that corresponds to the total area, the sum of these rectangular strips, the total area of that histogram, which is very nearly equal to the area under the curve, which is this integral. Yeah? So now you know how to find the area under the curve fx. What you need to find is the antiderivative of that function, right? Which is capital F. And then all you need to do is take the difference in that antiderivative between the limits a and b. Yeah?
Okay, I get it,
Know?
sir.
Okay.
Yes, sir. Thank you.
I hope the rest does as well, but eventually, I mean, it takes some reflection, I suppose. I mean, it's It's not that that you can learn this in
Darren,
an
good
instant.
morning. Someone is asking if
The
we're
rectangle.
finding
Yeah, so the triangle is just a visual aid, right? Just imagine you move from left to right from this point on the curve. So you leave the curve. To return to it, you have to go up again. You have to go back to the next point, right? So there's a rise and there's a run, and the ratio of the two is equal to the gradient of that straight line here, which is the linear approximation to the curve at that point. All right, so I'll leave that for you to contemplate. But as we move on to the other one, let's see. This, oh, back to the slides now. Okay. It's a problem with this BBC platform. Every time you come out of this, you're back to square one. So, oh boy. Right, I think that's where we were. Okay. Right, so this is where we left, right? So what I was trying to explain is this rule here. To find the area under a curve, fx, between x equals a and x equals b, we have to find the antiderivative of that function and then simply take the difference between the function values of the antiderivative between points a and b. Now what we will furthermore need is a couple of rules for differentiation. So there is what we call a chain rule that we will frequently use, which is when you have a compound function, which is f in this case, you have a function g which depends on x, and then you have another function which is a function of g, so it depends implicitly on the variable x. Now to find the derivative of f with respect to x, the first thing to do is see how the change in x affects g. So that is dx causes a change dg, right? And since f is a function of g, the change in g causes a change in f, df, right? So this is, well, if you write it like this, dg by dx times df by dg, you see that the dg cancels out. So you get your df by dx, and this is known as the chain rule, right? Just to illustrate how it works, suppose that your gx is the function a times x squared, you see here, right? And the function f is the exponential function, e g in this case, right? So what you get if you combine the two, so write f function of g, you substitute for g, a times x squared, and you get that, right? Now to find the derivative of this compound function, right, what you do is you apply the chain rule, this one here, and start off with f, g. The derivative of the exponential is the exponential function itself. It has that unique property. That is the e to the x function. The derivative of a times x squared, where we use the rule for differentiation of power law expressions, x squared, what you do is you take the index, put it in front, so the 2 goes there, and you subtract 1 from the index. So you end up with 1. So 2ax is the derivative of ax squared, right? Apply the chain rule, so we multiply this by that, and you get the derivative of the compound function exponential ax squared. It's 2ax times exponential ax squared. So that's another thing that you have to keep in mind. I know it's a bit steep, but of course that's why we advise you to do that calculus course in the maths department, right? Because this thing will come back over and over again, and it is just part of your well, education as a science student. You cannot get around this if you want to do anything meaningful in any quantitative science like chemistry. Right, let's see now. Let's go back to our first order. Okay, I see somebody says you were told you could do a course other than calculus. Well, I would not recommend that. I mean, stats, you can learn that like, well, this afternoon, right? But this needs some real training. In fact, you should have come with this knowledge already from high school. Don't know what they're doing over there. Okay, now let's apply this these rules of differentiation and integration to the rate law. Okay, so the rate law was minus dA by dt equals k times A. Right? You can reorganize this expression by dividing through by A. So you get rid of A here, you put it there, and then you put these summation signs, these integral signs in front. Now, what we have is now something that we should recognize. The evaluation of this integral then involves finding the antiderivative of the function 1 upon A. Now, the function 1 upon x in general has as its antiderivative the logarithm, or the natural logarithm of x. So the derivative of ln x is 1 upon x. That is a rule that I cannot explain here, but that's, you have to take my word for that, right? So to evaluate this integral, we have to take the antiderivative of 1 over a, which is ln a. And we take the difference of ln a between the limit of integration, which is the a, the concentration of a at an arbitrary future time t, and its value at time 0, which is a0. So we always have to specify the value of a at time 0 in order to predict the future course of the function a. Now, this integral is very simple. It is simple. Well, what you do is add up dt, 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 etc. until you reach point t. So the sum of these dt is then simply the final time t, right? You just walk through that interval from 0 to t in small steps, dt, and then add them all up, giving you t, right? So what we have done, that we have integrated the rate law, the first order rate law for this unimolecular reaction. Well, if you reorganize that term, so what you do is you put a minus in front of both sides, so minus kt on the right, and then you transpose the ln a naught, put it there with a plus. You have, in fact, the solution in this very convenient form, which we call this the integrated form of the rate expression, right? So we started off with the rate expression, which just tells you what happens at any particular time t when the function a has a value at. It tells you what happens during the next time interval dt, yeah? and so on and so forth until you reach a point where you want to know the value of a. Yeah, so avoiding that procedure, that very cumbersome procedure, we use the methods of integration, right? So that leads ultimately to a explicitly as a function of time. This is the initial value, a naught. This is the time at which you evaluate the function a t. And in this form, it's very easy to use because it has a linear form. If you look at the left-hand side, call that y. The right-hand side starts off with a constant c, and then you have a linear term, a constant minus rate constant times a running variable of x or t in this case. It's just a matter of relabeling, but you recognize this as the equation of a straight line, right? Now, in terms of a graph, it will look like this. If you plot the ln of the concentration of A at any time t versus time, right? Right. Yeah, that was a good piece of advice I just saw. There's a myriad of videos that explain this stuff. So just find a good one, and then you should be in good shape. Right. So the prediction is that for a first order reaction, the ln of AT varies linearly with time, and the rate and the gradient of that line is negative. It is the negative of the rate constant, right? And the rate constant is what we are ultimately interested in. So the rate constant can therefore be obtained by plotting a graph of ln AT versus t, and then evaluating the slope and put a minus in front of it, right? So that is how you process your data when you do an experiment on first order kinetics. And I understand that there's one on the program in the lab, right? Next week or something. All right, another way of representing this graph is by using the rule of combination of logarithms. Remember that rule of ln x plus ln y equals the ln of x times y, and ln of x to the a equals a times ln x. Now in this case, if you imagine a to be minus 1, so you have a times ln x, a is minus 1. In this case, put the a there as an index, right? So ln of minus ln of a naught is the ln of a naught inverse, and the minus then becomes a plus. Then you use the other rule of combining logarithms, which converts the sum of ln's into the ln's of the product. So we have the ln here of AT times a naught inverse, or in other words, ln of AT divided by a naught. Right? So if you combine those two logarithms, that's what you end up with, leaving minus kt on the right-hand side. So another way of plotting this is ln AT over a naught versus t. You see the constant here is gone, it is 0. That means that the line will now start at point 0 at the origin. Yeah? And from there it goes down with the same slope minus k, right? Sorry. I don't know how that happened, but I can zoom out, I guess. Right. Yeah, that's better. Now, of course, you can also plot A directly as function of t. Here we have it in the convenient form ln A equals ln A naught minus kt. What you do is you apply to both sides of the equation the anti-log operation. Yeah? In this case, since the base of the ln logarithm is that number e, we take the exponential of ln AT, where the exponential, which is the anti-log, compensates the log, so that leaves AT after that point. And you apply the same operation, so the anti-log to the right-hand side. So you get the anti-log of a sum of terms, and taking the anti-log of a sum is equal to the product of the anti-logs. So that is the product of the anti-log of the log of a naught, which is a naught itself, times the anti-log of minus kt. What you get is this. So a as function of t is equal to the A at the start of your experiment, or whatever it is, times the exponential of minus k times t, which as a graph shows this decaying exponential behavior. So if you start off at time 0 at value a0, right, then at any future time you will find that the concentration will taper off eventually to 0, right? Because if t goes to infinity, this function tends to 0, right? Yeah, so this is the explicit form of the solution of that rate law, the minus dA by dt equals k times a. This is what it eventually leads to. Now you see that as the concentration drops, the rate of change, so the rate of the process will also drop, because there's simply less molecules to react. And you see that the gradient of the tangent to the curve, which is the rate of the process with a minus sign, also decreases over time and eventually goes to 0. All right. But now, of course, we have an explicit solution of that rate equation. So we have integrated the rate equation. That is what it means. All right, now let's move on to having dealt exhaustively with the first order reactions. Now let's see what we can do with second order reactions. And we had distinguished two types of second order reactions. So these are the elementary one-shot reactions that involve the encounter of two molecules, either two different ones, A and B, or two molecules of the same type. So it is 2A goes to products. Let us first deal with this case, where the molecules A and B are distinct. And we, as usual, we write for the rate of the reaction that it is equal to the change in A, concentration of A in time interval dt, which is negative, hence the minus sign in front. And we write that as a function of the momentary concentrations of A and B. So it is always a rate constant, which is independent of those concentrations, only depends on temperature. And then a function of the concentrations of A and B at that point. Now, to justify the fact that for these second order reactions, the dependence is a simple product of A and B concentrations, just imagine that you were to follow an individual molecule A. So we have a reaction mixture with molecules A and B that collide, well, with the walls of the vessel in which the mixture is contained, but also amongst themselves. So A can bounce off another A molecule, then nothing happens because they don't react amongst themselves, or with B molecules, and then there's a chance that a product will form, right? If the collision is sufficiently energetic. That means if the temperature is high enough. But for now, let us just concentrate on the collisions that A and B undergo. So imagine you're riding along with this molecule A that dashes about and collides with other molecules, either A or B. Now, the likelihood of that A molecule colliding with a B molecule will, of course, increase with the number of B molecules present. If there are none present, it has nothing to collide with, right? But as you increase the concentration of B, so will the frequency of collisions. And that frequency of collisions will actually increase in proportion to the concentration of B. Yeah, if you consider a unit volume, say 1 liter, and the number of moles of B present, if you double that number within the same volume, the number of collisions that our A molecule undergoes with B molecules will double as well. Right? Now, conversely, if you increase the concentration of A, the number of A molecules that are colliding with B also increases, yeah, with it, and the number of collisions will increase in proportion with that concentration as well, as can be seen fairly easily. Or you could reverse the roles of A and B. So now we imagine that we are following a molecule B on its course, on its path through that mixture of A and B and products. From the point of view of B, the rate or the rate of collisions, the number of collisions per second, will increase in direct proportion to the number of molecules A present in that fixed volume of 1 liter. So we find now that the number of collisions between A and B molecules, which in turn is proportional to the rate of the reaction, R, right, is proportional. That rate is proportional to both the concentration of A and to the concentration of B. In other words, it is proportional to the product of concentration A and concentration B. So that is how you arrive at the rate law for the bimolecular case, elementary reactions, second order reactions between two unlike molecules, right? So we have minus dA by dt, which in this case is also the same as minus dB by dt, because A and B disappear at the same rate. Yeah, for each A that is lost, one B is lost as well, and vice versa. And that rate must be equal to the rate constant times the product of the concentrations of A and B. So it's a bit more complicated than the unimolecular rate law, as you can see. Now, this argument can be extended to case 1, where the reaction is one between two like molecules, two A molecules. According to our convention that we have already established, we formulate the rate as the rate at which the concentration of A decreases, so dA by dt with a minus sign, multiplied by 1 over the stoichiometric coefficient, which is 2 in this case. So because in each reaction event, 2 molecules A are lost. That means that A disappears at twice the rate at which the products appear. And if we define reaction rate as the rate of appearance of products, then we numerically will have to equate that to the rate of loss of A in unit time times 1/2. Using a similar argument, not exactly identical, it's a bit more subtle in this case, but that will be explained more fully in the more advanced course on kinetics. You get something that looks similar to, or very strongly analogous to that for case 2. So in this case, you have A equals B. So A times B becomes A squared in that case, right? So this is the form of the rate equation for second order reactions, which are homomolecular reactions between two similar molecules, right? Again, if we want to find what this implies for the time course of that concentration of A, so we start off at time 0 with concentration A at 0, and ask the question, what will be the concentration of A at any future time t? Then we start off with the rate law, this one, reorganize it a bit, and then apply the technique of integration, right? So the first step will be to move A squared to the left. So we divide the equation here by A squared on both sides. So we cancel it here and put it there. And then multiply by 2 times dt on both sides as well. So you cancel the 2 dt here and you put it there. So that is how you end up with this. So minus dA by A squared equals 2k dt. In this form, we can apply the technique of integration, because we have separated the dependent variable A from the independent variable t, right? So we can perform integrations on both sides of this expression on the individual variables a here and t there. Let's see if that is, and that is what has happened here. So we have put the integral, the summation signs on both sides. So at time 0, we have a concentration of A equal to A0. At the future time t, its concentration is the unknown A at time t. Right? Now, again, the integral on the right-hand side is trivial. Yeah, it is again t. 2kt is what you end up here. The one on the left is a bit more problematic. It is mathematically, it is the question of finding the antiderivative of the function 1 upon x squared, or x to the negative 2. Now, here we can apply again the rule for integration of a power law function. That is, if you have x to power n, to find the antiderivative, you add 1 to the index, and the new index you put, or the inverse of the new index is put as a factor here. So -2 is the index here, so you add 1 to it, so you get x to the -1, and you divide by, by -1, the new index, so that gives -1. So minus x inverse, or -1 upon x, is the antiderivative of 1 upon x squared. Conversely, of course, you could go back and say, well, if this is the antiderivative of that, then the derivative of this must be that. Yeah. So if this is the antiderivative of 1 upon x squared, yeah, then the derivative of -1 upon x must be 1 upon x squared, as indeed it is, because this is minus x inverse. To find the derivative, you put this -1 in front, cancelling the -1 that was there, and you subtract 1 from what was there. The -1 gives you -2, right? Good, so applying that to this expression here, we now have the antiderivative of 1 over a squared. It is -1 upon a, right? We already had a minus in front there, so that carries over here. The upper integration limit is a, the lower one is a naught. This right-hand integral we evaluated already because it was trivial, 2kt. These minuses here cancel, so then you end up with this. No? So all we need to do now is substitute the final value, at, gives you that, and then minus from it 1 upon a naught, yeah, this one here, and that is equal to 2kt, and then you transpose the constant term, and you find that the integrated rate law for the second order homomolecular reaction, right, is given by this expression, again in a convenient form because it is linear, right? The reciprocal of the concentration of A at T, if you call that Y, the dependent variable, equals a constant, which is 1 upon the time 0 value, right? Plus a constant, 2k, let's call it m, times the running variable t, the independent variable t, which you can also write as x, right? So you have something of the form y equals constant plus another constant times x, which again is the description of a straight line, an intercept c at time 0, and a gradient 2 times k, twice the rate constant, right? And the running variable is the reciprocal of the concentration of A. So that suggests that if from an experiment you obtain a time series of a concentration of compound A that undergoes that bimolecular process, that second order reaction, right? You would process your data as follows. You would, for each time, you calculate the inverse of the concentration of A, and you plot that versus T, versus time. No? So if the reaction follows that particular kinetic scheme, so 2A goes to products, then what you should obtain is this straight line with a gradient equal to 2 times the rate constant and an intercept to inverse of A naught. Yeah? But the important one is always the gradient, because from that we can infer the value of the rate constant, which is what we are usually interested in. So the rate constant in this case will be half the gradient of that plot, the plot of the integrated rate law. All right, now let us sum up. Right, so let's compare again the rate law, which is always the starting point, versus the integrated rate expression, right? Now, a rate law that tells you just what happens at a particular instant. You have a reaction mixture of a particular composition, and what the rate law tells you is that if you come back, say after 1 second or an hour, depending on how fast the reaction is, what will it look like? What will that mixture look like? But only within a small time interval, immediately consequent upon the first moment of observation. The integrated rate expression gives you the value of, well, gives you the composition of your reaction mixture at any future time, right? So that is where we need the technique of integration. And most importantly, it allows you to analyze your data in a form where you can extract a value for that rate constant and the order as well of the reaction, by plotting the appropriate graph. So for example, if you were to plot if you were to work on the assumption that the process is first order rather than second, you were to make a plot of the logarithm of A versus T, and you would expect a straight line, right? If you don't get a straight line, you get a curve instead, you know that your assumption was wrong. So what you do now is you assume that it is second order, in which case you make a different plot, this one, this versus that. If now you get a straight line, then you can stop there and say, well, apparently now my second hypothesis was the correct one, and I can now proceed to find the rate constant as well. Right? So that is how these integrated rate laws are used in practice. And in this case, it's only for very simple processes, but of course it gets more complicated if you look at mechanisms, right? But that is something for future concern. Okay, I think it's almost 10 o'clock on the dot, so I think I can stop the recording here. Mm-hmm.